Hello everyone, I am Siddharthan. Currently we are in the first module of our deep learning course, and in this first module we have discussed about some of the basics such as what is meant by deep learning and a neural network, what is meant by a perceptron and how to build a perceptron from scratch. In this video we are going to discuss about one of the critical aspects of neural network, which is activation function. So here first let's try to understand what is the purpose of an activation function, what is meant by it, and the different types of activation function, and also when to use which type of an activation function. So that will be the agenda for today's video, and let's get started. So before going into activation function, we first need to clearly understand the basic working of a machine learning model, and that will help us to understand these activation functions in a better way. So for this, let's just take a very simple example. Let's say that we have years of experience of several people and the salary that they make, right? So let's say that given years of experience of a person, we need to predict their salary. So this is the use case. Here your x-axis, years of experience, will be your feature, and the target that you are predicting will be your salary, right? So let's say that we want to do this manually. So what we would do is, let's say we have a data set, and we would plot this salary against his years of experience, and let's say that this data point represents a person with 2 years of experience and their corresponding salary, let's say $100K or something, right? So similarly we have other data points. So given a new years of experience for let's say a person, we need to predict the salary that they are going to make. So how we can do that is, we could find a best fit line that kind of goes through or close to all these data points, and that will be the equation that relates the years of experience and the salary. Let's say that line's equation is y is equal to mx plus c, right? Now if we have an unknown data point that's not present in this data set, and let's say the years of experience is 5.5 years, we could just plot that in this particular graph. So let's say that this is where 5.5 years is, and we would see where this 5.5 years of experience meets this red line, and the corresponding salary we would find here. So this is the ML models work as well. So first you would give it the data set that you have that kind of has this years of experience and let's say the salary, and it tries to find the best line or the curve that passes close to all these data points. So this is what happens when you call model.fit in sklearn, right? So this is what happens there. So once you have that, you have an equation that relates these features and your target variable, and then you have a model that is trained, and you can pass like a new data point and call the predict function, and it would give you the target variable. So the only complexity is, in this case we just have one feature and one target. In the case of models and machine learning use cases, we would have like 10, 100 or even thousands of features, right? And this is an example of a linear relationship where your target kind of increases when your feature increases as well. In other words, your salary is going to increase when your years of experience is going to increase, right? So there is a linear relationship. And again, we also have machine learning models that kind of capture non-linear relationship as well, but neural networks does it in another level, right? So that's where activation functions are really helpful. The main purpose of activation functions in neural networks is that they can add this non-linearity component to the neural network that lets the neural network to learn from more complex relationship. So this is a simple relationship, right? So this is just like a straight line, a linear algebra thing. But when it comes to, let's say, image recognition, speech recognition, and much more complex use cases, the data, the features and target are not going to be in a linear relationship all the time. In order to tackle this, we need to make this model in such a way that they can capture complex relationship between the data points. So that's the main purpose of having this activation function. Now let's try to kind of understand this with a proper definition and like how this comes into play in a neural network. So an activation function is a mathematical function applied to a neuron's processed input, transforming the neuron's output to the next layer in the network. The primary purpose of an activation function is to introduce non-linearity into the output of a neuron, which enables the network to learn complex pattern during training, right? So maybe first we can understand the second part of this definition, which we have just seen, right? So the main purpose is to add this non-linearity component to this neural networks, right? So that it enables a network to learn complex patterns during training, right? So this we have seen. And now let's understand this definition itself. So it is a mathematical function, or you can think about it as a mathematical equation that applied to a neuron's processed input. So when I say processed input, we have already seen this in the perceptron video in the previous videos. So let's say that this is a single neuron, or what we call as a perceptron, right? So this is how a neural network would look like. So let's say you have an input layer, you have two hidden layers and an output layer, and there are like individual neurons in each of these layers. Let's take this particular neuron. So this individual neuron is what we call as perceptron, and this is how it would look like, right? So let's say that we have three inputs kind of passing to this particular neuron or the perceptron. We have x1, x2 and x3, and each of these input variables, these input features, will be having an associated weight to it, right? So let's say w1, w2 and w3, and in this perceptron what actually happens is we do a weighted sum. So it's like we multiply this x1 and w1, add it to the product of this x2 and w2, and again add it to the product of x3 and w3. So it is a weighted sum of the product of your feature and your weight, and then you add a bias term to this. So this is your weighted sum. So this is what I call by processed input. So now you have a processed input, which is nothing but a weighted sum of these features and your weights, and then you add a bias to it and apply it to this activation function, which is basically a mathematical function or a mathematical equation. So this determines how this output is scaled, or how this input, this process input or your weighted sum is basically like processed, and what's the output you're getting. So that's the function of this or the purpose of this activation function, right? So this is for single neuron. So similarly, when you put the same concept in a neural network, so this is the input layer, so we don't have activation functions here, let's say, and this x1 and x2 are passed to the neurons of the next layer, right? So we have these three neurons over here, and let's say this z represent the weighted sum and the f represents the activation function. So we would have weights, and these weights will be constantly changed during the training process, which is basically what training is, right? So when a neural network or a machine learning model is trained, what basically happens in the training process is the weights are constantly updated so that you have the best model that could give you accurate results, right? So your weight would constantly change, and we have this weighted sum, and we apply this activation functions to this. Now your activation function changes your value that's going to pass to the next neuron. So let's maybe understand here. So this is one neuron, so you have some weighted sum, and let's say that value is coming out to be 100, the weighted sum, and this activation function can change this value, let's say, to 0 between, like, let's say 0 and 1. So when you pass a value, it kind of maps it between 0 and 1, and that kind of input passes to the next neuron. So similarly, all these things happens here. So that's what is meant by an activation function. So it is a mathematical function applied to a neuron's processed input, transforming the neuron's output to the next layer in the network. So it basically dictates what is going to go to this next neuron, right? I hope everyone is clear until this point. Now let's see how these values are changed, what is the range in which these values will be changed, and the different activation functions that we would have. So if you have built like basic neural networks using Keras, TensorFlow, or even PyTorch, right, just you would have came across activation functions like sigmoid, ReLU, softmax, etc. So that's what we are going to see. So I hope that everyone is clear until this point. Now let's understand the different types of activation functions, and maybe when to use which one in a high level overview, and maybe in the next video let's go in detail about the formula for each of this activation function, and we can also do an hands-on part where we could build like manual functions in Python and give in some values and get the output for this. Okay, so these are the four main, or like, let's say, widely used activation functions. Again, there are a few others as well, but these are like the widely known ones. So first we have a sigmoid curve or a sigmoid activation function, right? So this is just similar to how your logistic regression model would work. So this is the properties of a sigmoid activation function. So given a value, given a processed input, which is the weighted sum of your feature and your weights, it transforms or it maps that particular value between 0 to 1, just what a sigmoid would do, right? So when you give a value, it will kind of put it between 0 and 1. So this is the curve of a sigmoid function, which basically looks like a S shaped curve, right? So in a logistic regression model, right, when this y value or your sigmoid function value is greater than 0.5, we classify it as class 1, and if it's less than 0.5, we classify it as like class 0. So similarly, in neural network, sigmoid curve or sigmoid activation function is widely used for the output layer of binary classification, where it basically sends you whether it's class 0 or class 1 by just sending the probability. Again, if the probability is more than 0.5, we are going to say it's class 1, and if it's less than 0.5, we are going to say it's class 0. So I mean, this is about sigmoid thing. So the main thing that you can remember are, it gives you the value in range of 0 to 1, no matter what the value you are passing. It can be 0, it can be a negative number, or it can be like, let's say, 100, 200, or even large positive numbers. So it's always going to be between 0 to 1, right? And it's again widely used in the output layer of binary classification problem. And the one disadvantage of the sigmoid activation function is that it's susceptible to this vanishing gradient problem. So this is an interesting case, and we need to understand what is meant by this vanishing gradient problem. I can explain you this in a better way with this analogy. You probably would have heard about this whisper challenge, where let's say that there is a queue where 10 people are standing, and let's say the first person standing at the back kind of whispers a statement to the person standing in the front, and that person would again whisper this to the next person, and this would go on. And what would happen here is that at each step, let's say the statement is going to change a bit, right? Because they are going to hear it only once, and the final, if you ask the final person, the statement would have kind of changed, right? So vanishing gradient is also similar to that. Maybe let's understand this with this neural network figure. So in neural network, when we train, there is something called as forward propagation and backward propagation that happens. So it's basically like how your messages are passed during a whisper challenge. So the only difference is that here the message flows in two directions. So it goes in this forward direction, which we call as forward propagation, and it also comes back with the feedback whether the predicted output is correct or not. So basically that's how your weights are adjusted, right? And when you use a sigmoid activation function, right, so in that case what would happen is, the gradient is nothing but how your loss function changes with respect to your weight. So if you are clear with, or if you have already seen my machine learning course, you would probably know this one. So in gradient descent or optimization, we try to minimize the loss function by changing these weights, right? So we try to change these kind of gradients, which is this again derivative of loss function with respect to your, let's say, weight, and you would have this minimum gradient. So basically what would happen is, in the early layers, let's say you have 5 hidden layers, one output layer and one input layer. So the information goes in this way, where your weights are changed and it comes back again, and in the backward propagation also the weights are changed. So when you have a smaller gradient in the initial layers, right, so your gradient is going to be too low, and because of that the change in weights are not that much high. So this is what we call as vanishing gradient, because your gradient is low. So basically what happens is, your training time is going to kind of go high. It's going to more time to train to reach that convergence, and again it's not going to be that accurate, the model. So this is what we call as vanishing gradient problem. And this sigmoid has this problem because this can have like lower gradients when it reaches this higher peaks of around 1 and around 0 and so on. So this is like about sigmoid activation function. And the next activation function is ReLU, which stands for rectified linear units. So this is one of the widely used activation functions in neural network, and this is mainly used in the hidden layers of the neural network. And here the value that it's going to send to the next in the neuron to the next layer is that 0 to infinity. So in the case of sigmoid, it can only give the output values of 0 to 1. When I say output, it's not the final output that you're saying, but what's even passed like from each of these neurons. So sigmoid is going to send you the values between 0 to 1, but ReLU is going to send you values between 0 to infinity. So what this basically means is, it basically applies a threshold to your processed input or to your weighted sum. So when the weighted sum is more than 0, it's going to give that actual value. Let's say the weighted sum is 1. In that case, it would give the output as 1. If the weighted sum is, let's say, 1000, it's going to send that 1000. But when the weighted sum is less than 0, that means when it's a negative number, it's always going to send 0. So that's why you have this curve which kind of has this flattened line over here, and then you have a straight line here. So this is an example of a non-linearity, right? Because it's not always straight. So you have this non-linearity where it has this threshold, a straight line here, where it basically sends you the output as 0 when it's a negative number. The processed input or your weighted sum is negative number, and when it's a positive number, it's going to send that particular value. So this is about this rectified linear units, and this actually computationally efficient. It's going to kind of fasten your training process. When, let's say, you use a sigmoid activation function in some of the neurons, and instead, let's say, you're using a ReLU, it's going to take like lesser time, and it's computationally efficient as well. And this mitigates the vanishing gradient problem, because in a ReLU, right? So the gradient is constant. So gradient is nothing but the slope. In a straight line, in this case, the slope will be 1 for all the positive outputs it's sending, and it will be 0 for all the negative numbers, because here the slope of the straight line is going to be 0, right? So this mitigates the vanishing gradient problem, because your gradient won't be too small in this case compared to a sigmoid curve. So that's like the main advantage of ReLU, and it's like again widely used instead of sigmoid in the case of hidden layers, right? So that's about it. But the other disadvantage for this ReLU is, when most of the data points gives you this weighted sum as a negative number, your neuron is always going to give you 0 as the output. So basically we call that term as like not firing. So most of the neurons in your network may not fire. When I say it may not fire, it would give you the output as 0, because the weighted sum is a negative number, right? So this is what we call as dead neurons. So this ReLU has this susceptibility of having this kind of dead neurons. Again, this varies from use case to use case and data to data, so we can't clearly say that this is when this would happen, but we just have to kind of remember all these pros and cons of each of this activation function. But ReLU is like a widely used one. And there is another kind of advanced activation function that's related to ReLU. We call this call that as leaky ReLU, where it allows like a small negative values, right? So let's say that if we are getting like a negative number, it's not going to be a large negative number. It just allows like a small negative number to be sent out of this neural network from this particular neuron. So that's like the other activation function that you can do a research. But again, ReLU is widely used. And then tanh is another activation function, but I mean it's not like that widely used as ReLU or even sigmoid. So here it would gives you the value between the range of -1 to +1, just like the tanh function. So here this is how a curve would look like. So it's similar to sigmoid, but sigmoid is around this 0.5. The lower end is 0 and the higher end is 0. But tanh is going to give you the higher end is +1 and the lower end is -1. And you can see it is 0 centered, right? So the max value is 1 and the less value is like -1, so it's 0 centered. Again, it's kind of used in some of the use cases. I mean in RNNs it's kind of used in few cases, but again it's not like that widely used, and it's also mainly used in hidden layers in some cases. Again, it's also data set specific and it's like task specific, so we can't like clearly say that this is when it kind of has to we have to use the standards. So it's used when, let's say, you want your neuron to send negative values like this one, right? So that's when we kind of can have this tanh, but again not that widely used as ReLU. And then we have this another widely used activation function, which is softmax. And this is like really, I mean like mostly this is used when we have a multi-class classification problem. We use this in the output layer, and this would give you the probability value. So let's say that we have 10 classes that we want to predict, and in the output layer we would have 10 neurons, and each neuron would give you the probability of, you know, what the probability of the data point being a particular class. So let's say that this is our output layer and we have 4 classes, this green thing, let's say that this is our output layer. So if we have used a softmax activation function, right? So this when this neuron has the highest value, that means that the data point belongs to class 1, and this, if this has the highest probability, it means that that data point belongs to class 2, and so on. So each of this would give you the probability of that data point belonging to that class, and when you add all these things you would get like the sum as 1, which is just the probability value, right? So that's about it. So the range is going to be the probability, and which is between again 0 to 1. And output layer, it's mainly used in the output layer of multi-class classification problems. And again, this would convert the raw values that you get from this weighted sum, and this would convert this to a probability, right? This is about again softmax activation function. As I said, these are the widely used ones. So we may mainly use ReLU, sigmoid, and softmax. So let's say a sigmoid in the output layer of your binary classification, ReLU mainly in the hidden layers, and softmax in the output layer of multi-class classification problems. So that's about it. And I'll just added this table so you can like quickly refer to this one. So we have the sigmoid that has this output range between 0 to 1. And it's effective for binary classification, just like it's just similar to the logistic regression model. And this you need to use with caution. As I said, it can lead to the vanishing gradient problem. And the next one we have is ReLU, rectified linear units, and the other variation of this is leaky ReLU, where it allows like slighter negative values. And here the output range will be between 0 to 0 to infinity, because like if it's a positive number, the weighted sum is a positive number, it's always going to send that number directly. So there is like no change to this, and this is widely used in the hidden layers. And again, it's like a popular choice as it kind of computationally efficient, and it also solves the vanishing gradient problem. And then you have this tan h, and here the output values ranges from -1 to 1. So this is not -1 and -1, this is -1 to +1. So you can think about it like that. And this is zero centered, right? Because your lower kind of extreme is -1 and your upper extreme is +1. So you can use this whenever you want a zero centered output. And again, this is less common. And finally, you have a softmax activation function that would also give you the probability. So your value will always be between 0 to 1, and when you sum it up, you will get the value as 1, and it is used in the output layer of multi-class classification problem. So this is about activation function and its types, and I hope that you are clear about what we have discussed so far. And in the next video, let's understand the math behind it and how these output values are getting calculated by understanding each of the formulas for these activation function. And let's also build like simple functions in Python, give some values and get a value out of this, like the process value out of this activation function. So this would help us in order to understand the working of a neural network better, and to understand which activation functions can be used and how we can kind of handle these neural networks in a better way. So that's it from my side, and I'll see you in the next upload. Thanks for watching.